All right, welcome back everybody to MCAT physics. Today is about fluids. This is my least favorite chapter in like all of MCAT, bro. I hate this more than cars because here's the thing. It's like, I don't know, it just gets really confusing. So what I'm gonna do is I'm going to tell you the stuff that I actually know, and then for the things that I don't know well, I'll just throw in the formulas that I know, and then I'll just like, that should be enough, right? Because most of physics is knowing formulas. The only issue I have with fluids is like, I know the formulas, but then like they just don't work sometimes. So this is kind of like a YOLO, but don't worry, it's not as bad as it seems, and I don't think this is as high yield as the other chapters. So yeah, let's just begin. All right. So do you guys know what a fluid is? Like, what is a fluid?
Water.
Is it just water? Like, is it just liquid?
Let
me write some stuff. We got solids, and then we got liquids. What is water? It's a liquid.
Yep. And
then we have gas. So a fluid, like I always think of fluid as liquid, but it's liquid and gas. What is the difference between liquid and gas? Liquids, they will, actually, do you know? Like other than, like I know they're different things, but like what's like different in terms of their features?
Like the particles or like the boiling points or?
So like other than, I mean it involves the particles. Like I know liquids are closer together than gases, but what about like, it's okay, I don't even know how to ask it without giving it away. So I'll mention it. Basically, liquids and gases, they both don't have a definite shape. Liquids, they'll take the shape of their container. And gases, they will, but at the same time, if your container is this big and you have one that's this big, they're going to like fill in that container, right? So gases don't have a definite volume, whereas liquids do. Gases are compressible and what's it called? They're compressible and whatever the opposite is. Liquids are not, they just stay the same. So they have definite volume and they take the shape of the container, but as much as they can. Whereas gases will also like expand or compress if they need to. And then solids are solids, I'm not gonna write about that. But a fluid is basically like liquid or gas. And this is a main formula for today, not really, but like it's a big one. This P, when I write like with the circle, this is the Greek letter rho. P is density, all right? I might just call it P, but it's a rho. This density, because we don't use D, we use this, if you want to be like really big time physicist, this is density equals mass over volume. If you ever forget this is what I was taught like a long time ago. I'm gonna put a D over here. This is how you can change between density, mass, and volume. So if you're trying to find density, you take what's left, mass over volume. If you're trying to find volume, it's mass over density. If you're trying to find mass, it's density times volume, and whatever other variations of that there are. That's the density. What's up? The density of water, it's 1, right? But it's more than that. So it's 1 grams per centimeter cubed. What is 1 centimeter cubed equal to? If y'all remember, I mentioned this like I don't know, a couple weeks ago when I started physics.
Milliliters.
Yes. This is also 1 grams per milliliter, and then 1,000 kilograms per liter. Or not liter, sorry, meter cubed. So know these, clearly I forgot, but know these conversions and stuff. Basically, a centimeter cubed is a milliliter. That's good to know. And then, you know what I'm saying? Because density of water, we always think it's 1 of something, right? But depending on what you're given, it could be 1,000. So just make sure you're able to tell what the density is based off of the units you're given. Can you open the thing back up? I like when it's dark outside. Oh, thank you. So we all know force is mass times acceleration, or let me put the G. Mass times gravitational acceleration. But another way we can write this is this right here. Why? Because rho times V is mass, right? This times this gives you your mass. So this is the same thing. Just know this because there's lots of times where they'll give you, like they won't give you the mass, but they'll give you density and volume, and they'll ask you for the force on something or something else, right? And you can easily figure this out, all right? That's force. Something small I want to mention is something called specific gravity. Specific gravity, it's just the density of I'm gonna put like substance. Density of substance over density of water. So it's always going to be density of water at the bottom. So, okay, here's what I'm trying to say. If your substance has a density of like 0.7 grams per centimeter cube, then the specific gravity is this. You might be wondering, what's the point of specific gravity if it's going to be the same thing as the density? I low-key forgot, but there's something, it's supposed to help simplify calculations at some point, but that's too beyond me, that's too advanced. So all I'm gonna tell you is just know what specific gravity is. It's going to be density of a substance over density of water. Usually it will just be the same thing, but what if I gave you this right here? What if I said the density of a substance is 777 kilograms over liter? Sorry, meters cube. Why do I keep doing that? Kilograms over meter cube. What is the specific gravity of this right here? No. Look at the units. What?
What?
No. 777. This is the density of A divided by 1,000. Because density of water with these units is 1,000.
Convert it.
Look, I'm using kilograms over meter cube.
Right, which is the same thing as one.
What?
Uh-oh.
No, I'm kidding, bro. You got this.
Wait, what?
No, I actually see where he's confused. Because you see how you got the density of water, you go 1 gram per centimeter cube,
Yeah.
1 gram per milliliter cube, and you bumped up to kilograms, and you wrote 1,000. But if you go from grams to kilograms, shouldn't you like divide by 1,000?
It's because this is meters cubed, so it's not the direct. It's not milliliters. Is that what you got confused on?
I think so, yeah.
Oh, okay. Well, there you go. I was trying to confuse you. Not with this, but like with that. So what I'm trying to say is that thing was really simple. If you're using grams over centimeters cubed or grams over milliliter, then it's going to be the same thing. That's your specific gravity. But if you're dealing with kilograms over meters cubed, where your density of water is not 1, it's 1,000, then it's not going to be the same thing. What is this going to be? What is the specific gravity of this? Like, what is this divided by this?
0.777.
Yeah, it's just that, 0.777. Let's put 0.78. So, yeah, okay, as far as I remember, there's one question that was on Question Bank that involves specific gravity. I actually don't remember off the top of my head, but it's very, very uncommon to see specific gravity, but just know it, keep it in the back of your mind.
Wait, so the units for the 1,000 would just be kilogram per meter cube also?
Yeah, this one right here.
Oh, okay.
Hey, Safe.
Yeah,
So I know you wrote the rho up there, and the P is the density.
Yeah.
So what do we use to like indicate pressure?
I'm about to talk about that. It's just a capital P. So, okay, this is how I draw P. You see what's like flat over here?
Yeah.
My rows look like this, where it's like a circular thing.
Oh.
But yeah, that's like, it gets really annoying. That's why I like to use D for density, but I've become very physicist, so I use rho. But just, if I'm writing it, I'll try to make it like obvious.
Okay.
So the next thing is going to be pressure. What is the formula for pressure?
Force over area.
Yeah, pressure is force over area. And the units, oh my god, the units for this is pascals. Or you can do newtons per meter squared. So newtons per meter squared is the same thing as 1 Pascal. And then that's the SI unit, but what other ways can we talk about pressure? Like what other units can we use for pressure? I mentioned this like in Gen Chem.
Maybe just a guess, like a mass, mass over volume.
What would be units?
No, what?
What would be units?
Like we have pascals and what else? I know you know this. We talked about this one time. Here, I'll give you one hint. 760. This is your hint. Yeah, torr. So torr is one of them.
Atmospheres.
Yeah, torr, ATM, millimeters, mercury, and there's some other stuff, but these are the main ones. So, and then kilopascal is just a pascal times 1,000. So let me make the unit conversions real quick. We have 1 ATM equals 760 millimeters of mercury, which equals 760 torr, which equals 101. I'm just gonna keep it as 10130 just because for MCAT we're trying to estimate and stuff. But 101.3 or 101,300 pascals, which is the same as 101.3 kilopascals. I think that's. There's other stuff, like I've heard of something called a bar and some other things, but these are the main ones you have to know. But definitely do know these because every now and then it shows up where you have to convert from one to another. And the cool thing is millimeters of mercury and torr are the same. Yo, do you have any markers? Or did you leave your stuff? You got strapped up with markers, bro, for real?
I already have this one.
Yeah, I already have blue. It's okay. I think one lecture, I'm gonna just use the same color the whole time. So for this, okay, there's this formula that looks like this. This is formula for absolute pressure. I can't elaborate on this, but just know this formula. This is total pressure, this is probably like initial pressure, and then this is just typical PGH, right? This is density times gravitational acceleration times height. There's another one that looks like this. So absolute pressure and gauge pressure, the only difference is gauge pressure is subtracting the pressure of the atmosphere. The difference between gauge and absolute, like gauge is supposed to be this is what my understanding is. You have a system and this is like the gauge, and then if you're trying to find the pressure of just this thing, then you're subtracting the atmosphere, whereas that absolute pressure is accounting for the atmosphere and this thing. That probably made no sense, but it's something like that. But in my, from my observations, I've never seen this stuff show up. The only thing that I would definitely know is just that this formula right here exists. Because a lot of times they just have you equating things like where it would be like this. Oh my God, something like this. Okay? Yes, you good?
Yep.
All right. Now, something that I actually do like, give me 1 second. I'm gonna draw something and then I'll show you like an equation. So let's say this area is like 10.
Isn't there like a Bernoulli something or
That comes later.
Oh, okay. So in what instances would you know like you have to set them like equal to each other?
Okay, that's just context based. Like what I'm trying to say is like, I don't think you were here when I gave the little intro, but for these equations, like, dude, I don't know, bro, it's just YOLO. Like, you'll know when to do it. If they give you 2 sets of each thing, right? They give you 2 sets of densities, 2 sets of H's, like heights and all of that, and like pressures and all that stuff, then you'll know to equate. If they only give you 1 set of things, then you will know to just use 1 time. Does that make sense? So I didn't come strapped up with questions for this chapter, so I'm sorry, but it's just one of those things. As long as you know the equation, you should be chilling for the most part. And then it just, over time with practice, you kind of realize like how these things work. For this one, this thing is pretty cool. This area of like this tube, this is all part of the same thing, but this like tube thing is 10 meters squared, right? And I just put 1,000 for this one. Basically, let's say I applied And there's liquid in here. Let me draw some liquid real quick. There's liquid in here, and this is another platform. If I push down that 10 meters squared platform with, let's do 50 newtons of force, what do you think will happen to this one? This will get pushed up, but do you think the amount of force is going to be higher or lower than 50? Would you say the same? What do you think?
I think the same too.
Okay, the answer is it's going to be higher. This one is an example of where you're equating two things. So over here, we're dealing with pressure. The pressure of this one is going to equal the pressure of this one. Pressure is force over area. I'm just going to write this out here. Yeah, it's already erased it, all right? So I'll call this as section 1, this is section 2. The first one is 50 newtons over 10 meters squared equals, let's put x over 1,000 meters squared. Because it's like, you have to make it proportional, all that, this would equal 5,000 newtons. So all I have to do is push down 50 newtons of force, and this will push up with 5,000 newtons of force. The reason I think this is cool, I asked ChatGPT this and said it's not possible, but I always thought if you're trying to, like, can you lift a car with a straw? This is my explanation. You can make something like this and make a whole mechanism or some, I don't know, big like chamber like this, and you make this tiny, like super tiny, like literally this big, and you push down. You see how you only push with 50 newtons and it became 5,000? That's because this area was small. So if you have a really small area and you push down with like a straw or some small stick, you push down like somewhat hard, like you know, like 50 newtons of force, and then you put a car on this platform that's with an area of like, I don't know, 30,000 meters squared, would that like make it shoot up or something? That's what I always be thinking. I don't think it's possible. There must be something that prevents that from happening. But that's why I think this thing is pretty cool. But that's what you should know. This is meant to make it easier to lift things. You have a small area where you can put relatively less amount of force, and in return, you'll get relatively higher amount of force to lift the other side. Because lifting this up with 500 newtons might not be possible, in whatever, or 5,000 newtons might not be possible. Any questions for this one? This is an example of where I was saying you have to equate two sides with the same equation. So force over area equals force over area, or pressure equals pressure. All right. Yo, you know the question that you asked? You know the question that you asked?
Yeah.
It was very simple. Like all you had to do.
The marshmallow?
Yeah.
Yeah.
Dude, these, what was it, UWorld? Their explanations are shit, bro. All you had to do was divide the densities. Because it's actually gonna relate to the next thing I'm gonna talk about.
Oh.
I mean, if you try it, you'll get the answer. I'm pretty sure. I didn't try it, but that's what makes sense. All right, so let's talk about buoyancy.
Dude, the thing with you were like, they do not show you no shortcuts.
That's
It's
the
like,
thing. I was like, what the hell are they showing?
The most fucking longest, most complicated route.
Yeah.
To get your answers, like, dude.
And then they include stuff that you've never seen before. Like, I don't even remember what I read, bro. It was cooked bad. Okay, let's talk about Archimedes' principle and buoyancy. So Archimedes' principle deals with buoyancy. I'll put FB, buoyant force. Basically, if you have this box and it's in a liquid, and let's say it's just sitting like this, then there's a buoyant force that's allowing it to sit like this, right? So you have like a buoyant force. This one can equal what we talked about earlier, rho times volume times gravity. This one I have to specify, all right? This density is, what do you think it is? Density of fluid or the density of the object?
Fluid.
Yeah, this is density of the fluid, not the object. The V is volume displaced. So not the entire volume of this box in this case, because it's not fully submerged. If it was fully submerged, then the volume of the box would be the volume displaced, but it's not fully submerged. So this one, I mean, it just depends if they give it to you or not, but they generally give it to you, or maybe you're solving for it. But the V is going to be volume of this water displaced by the amount of this object that's in the liquid. Let's do volume fluid displaced. and then G is just 10. So something to know is that if your density of an object is the same as the density of the fluid, what is going to happen? Like, is the box, the object going to float? Is it going to sink? Is it going to be halfway submerged or what? What did you say? Or I don't know.
No, I was just thinking out loud.
So, if you're, let me start backwards. If you're 1/4 density, so let's say we have this fluid right here, and then my box, right? My box's density is like, let's do like 20, whatever units, all right? 20, and then the fluid is 80, same units. Then my box, it's going to be somewhat submerged, but still floating. So let me see if I can draw this in a way that makes sense. Okay, I don't know if you can tell, but this drawing shows that this box is 1/4 submerged. All right, all I had to do was divide these. So 20 over 80 gives me 1/4. That means I'm going to be 1/4 submerged. And then if I'm half the density, so I'm 40 instead of 20, this is still 80, then I'm going to be halfway submerged. If it's the exact same, then it's going to be like submerged, but probably, I don't remember this exactly, but I think it's just going to be like chilling like right here. Once you exceed, then it actually like submerges and stuff. So it just depends on, I guess, how much higher you are than the fluid. But if you're less than the fluid, then find the percentage of the density, and that would be how much, how much elevated or how much below you are. So wait, Samir, you know that question that you asked? Can you tell me the exact values that it gave? It was like, was it 0.5 and 1.1 or something?
Marshmallow or box?
Actually, I have. Oh, you gave me another one? I think it was the marshmallow one. Oh, you sent so many. What the heck? Okay, what was the full question? It said mass and
so
stuff, right?
The volume of the marshmallow was 20 centimeters cubed.
Okay, I'll tell you this one. It was asking how much of it's elevated, right, above the surface.
So what percent of the marshmallow is above the surface of the hot chocolate? Yes.
Okay, all you gotta do, the mass was there to trick you. As far as I'm aware, all you had to do was divide the densities, just like what we were doing over there. If you do 0.5 over 1.1, this gives you about like, it's like around 0.45, right? So 0.45 or 45% of it is submerged, which means that 55% is above the surface or above the liquid. Does that make sense?
Yeah.
And then if you look at the overall explanation, it's so damn long, bro. I don't understand. All right, any questions on this stuff right here? All right, let's talk about.
Wait,
Yeah.
I actually had a question. So the density, volume, gravity thing that you put on that side. So I think your volume can be the volume of the fluid. Can you go over the volume aspect again?
Yeah. So
because I think that could also equal like the weight of your object or something.
I mean, it depends. So that's just like, so I'll tell you what this means from my perspective. Okay, actually, I'll answer your thing real quick. You're saying, or can you tell me the context? When will the volume equal the mass? Are you saying when it's somewhat submerged or fully submerged? Or were you not sure? You just thought? Like,
I just thought.
Okay, that would mean, like, okay, if your thing is fully submerged, then this V equals the volume of the object because the object's volume is what's displacing this, right?
Okay.
So if I am like 20 liters under the water, fully submerged, I displace the water by 20 liters. And if you want that to be mass, that would mean that the density is 1, like where your volume and your mass are the same, like 1-to-1. So don't look at it like that though. It's generally going to be volume, not mass.
Okay.
Okay, so another thing, right? What I said is only if you're fully submerged. If you're not fully submerged, and this is 20 liters, this box, your V is not going to be 20. It's going to be something else, like something less, like 5 or 10 or something. Does that make sense?
Yeah.
Okay.
because your entire box was not submerged, right?
Yeah, so you only displaced a little bit of the
Yeah.
volume, not all of it.
So say you displaced like, I don't know, maybe like 2 liters
Yeah.
with the fluid, then that would be the...
Then V would be 2. Yeah.
Okay.
These are like thermometers type things, but like not really. But you guys see the difference? This is, and these are both meniscuses, or I don't know how you say the plural,
Menisci.
but is it menisci? Okay. This one is concave, and I think that's the right word. Concave and convex. This one's going down. This one's going up. Anybody know? I feel like you would know. It's like some Anki shit, bro. Like, do you know what the difference is? Like, why one occurs over the other?
Surface tension and your capillary action, something.
Yeah. Can you? Okay. The words I'm looking for are
Cohesion,
cohesion.
adhesion.
Yeah.
Yeah.
Which one is which?
So the one on the left is, actually the one on the right is going to be your convex, and it's going to be cohesion, more cohesion than adhesion.
Mm-hmm.
And then
And
the
this
one
is
on
the
the
opposite.
Yeah.
Yeah. So these, when they're convex, it just means that your like fluid and whatever or particles are exhibiting more cohesion than adhesion. And then this one is concave, exhibiting more adhesion. So what's the difference between cohesion and adhesion? Cohesion is, this is right over here. Cohesion means molecules like binding to themselves, whereas adhesion is binding to like a surface. Like I'm talking about this surface right here. Okay, so for cohesion, you have a bunch of, let's just say this is water, they're binding to themselves. And I don't know, like in my eyes, like I just visualize when they're binding to themselves that they become like a peak like that. Whereas if they are binding to the surface, I guess now that I'm saying it out loud, it makes no sense, but it makes sense in my head. But anyways, just know that if you have a convex, meniscus, that means there's lots of cohesion occurring because all these molecules are binding to each other and they're just lifting this up. But if they are concave like this, they're going downwards, then there's lots of adhesion occurring, adhesion to the surface, whatever this surface is made out of, and that's causing it to, I don't know. I guess the way I'm thinking of it is like the edges are higher where it's binding to the surface, and then inside there's not much cohesion occurring, so it drops. I don't know if that made sense for you, but if not, it's fine. Just it's like a memorization thing then. And then which one is surface tension, or are they both? Which one do we normally associate with like surface tension?
Cohesion.
Yeah, so the convex one. All right, there's a couple more things in this chapter. Any questions up until this point? Anybody got? So this Venturi, this is called, I guess this shows the Venturi effect, which is, you can't tell by the drawing, but let me tell you what's going on. You're in an area that's like larger, and then as you reach this area that's smaller, do you guys know what happens to the velocity of the same amount of fluid? What? Up?
Increase.
Yeah. So as you go into an area that's smaller, your speed is going to increase. So it looks like this. This means that A and V, this is area and velocity, they're inversely proportional. So as your area decreases, your velocity increases and vice versa. But this thing right here is supposed to show pressure. So as you can see, while you're in an area that's smaller, the pressure is also decreasing. So let me write, okay, I'm gonna circle this, show. However, I need to ask something. When we talk about vasoconstriction, I'm talking about like the body in biology. Does vasoconstriction increase or decrease blood pressure? Bro, okay, yes, it increases blood pressure. But over here, when we have constriction, the pressure is decreasing. What the fuck? Why? It's okay. The thing is that
Isn't it that like maybe because like the fluid is just like moving so quick that it just like doesn't have time to like exert its effects to like increase pressure at the middle point?
it's probably something like that, but the simple answer is that blood is not an ideal fluid. All of these things that we talk about are considering that the fluids are ideal, but blood is not ideal, so it just breaks the laws of physics, like literally. So what I'm trying to say here is don't always apply things that you hear in physics to the body, because most of the time it just does not apply. So I'm gonna say it one more time, all right? For the Venturi effect, for ideal fluids, when we're talking about physics, decreasing the area or constricting will increase speed but decrease pressure, all right? But for the body, vasoconstriction will increase pressure. And I have no clue what happens to the speed, to be honest. It might be the opposite, but this is for the body. Okay, so this right here is like Bernoulli's principle. And this is just telling us that, okay, first of all, let me break this down. This is one side, right? This 1/2 rho v squared is your dynamic pressure, right? And then this P plus PGH will be your static. So you're combining them together, and you're basically saying that two sides will be equated. Once again, I don't know, I don't have a question on the top of my head on where this applies. But I do see this come up a lot. I'm gonna just tell you this, right? If you see velocity, you see pressure, you see height and stuff like that, and you see two sets of that, just know to equate them, right? Ultimately, they probably want you to figure out what the pressure of some system is. And so you just kind of know these formulas and apply them where you have variables that match the stuff, right? If you're given velocity, you're not gonna do pressure equals force over area, right? The pressure equation that that involves velocity is this thing right here, 1/2 PV squared plus this and all this, all right? So these, once again, I'm really sorry, I wish I could elaborate more, but I just don't know these that well enough to do that. So I'm just gonna keep this here and re-emphasize that usually you're equating two sides. So they'll give you a bunch of things and want you to figure out what the equilibrium pressure or something else is, okay? And the difference between Bernoulli and Venturi, I think Venturi is just a derivative of it or something like that. But Venturi effect in general is referring to that thing that I drew, where as you constrict and you're using an ideal fluid, your pressure will decrease and velocity will increase. Let's see what else. So one more thing. Actually, okay, y'all know what laminar and turbulent flow is? Basically, laminar flow is smooth and orderly. If you've ever used a faucet and you didn't, you didn't turn it on all the way, but you turn it on a little bit, at some point, it almost seems like the water is not moving. Have you ever experienced that? Yeah, that's called laminar flow. That's a true laminar flow, where it doesn't look like it's moving because it's so smooth and ordered. But if you increase that faucet, you open it all the way, then you're gonna start seeing this, right? It's just all over the place. This is called turbulent flow. So for laminar flow, you can predict the motion of waves and stuff, but for turbulent, you can't. It's just all over the place. I don't think there's much else to add for that one. There's some random equation I have in my notes, but I've never seen it ever show up, so I'm gonna just leave it out. But there's basically you know, you always start as laminar, but as you increase speed, then you become turbulent. That's like the most, I guess, you can know about this one. I hate this next equation. So this equation right here, Q is flow rate. I think the relation between this and like laminar and turbulent and stuff is that at a certain flow rate you become turbulent. This is just something like extra that we don't have to know, but it's, I guess, useful for physicists and whatever. But what you should know is just this equation. I don't think I've ever seen them ask you to solve a flow rate with all of these things because there's a lot to know, but you should be aware that our R right here, the radius, is raised to the power of 4. Because in general, what the MCAT likes to do is they'll tell you, if I increase this variable by 2, what happens to the whatever. Let's say I increase the radius by 2, what happens to the flow rate? And then they'll give you the options, like you double, you half, you increase by 4, you increase by 16. This is just a typical question, seeing if you know about the formula itself. What would the answer be? Like if I increase the value of radius by 2, what would the change in Q be based on these choices? 16, because 2 to the power of 4 is 16. So I've seen them do stuff like that. I've also seen them, I guess, I don't know, somehow incorporate this 8 and whatever. But if you can, I used to know this off the top of my head. I don't remember right now. But if you can, it's good to know this. But the least you should know is that R is raised to the power of 4. And this is relating to flow rate. If you're wondering what this N is, I don't know, I think it's called nu. I don't know, is that the Greek letters? Nu? Mr. Fat Boy, is that what it's called? I don't know. But this is it's not an N, it's like a Greek letter. But this is viscosity. Anybody know the unit for viscosity? Don't know how, oh, what's up?
There's no unit.
There is. I don't know how deep it is, but Pascals times seconds.
Damn it.
And do you guys know what the difference is between flow rate and then just like speed? Like flow rate sounds like speed, so what is flow rate? It's not that deep, but I've had someone ask me this before.
Volume per time.
Then what is speed?
Well, I guess flow rate would be like how much volume would be like per like, you know, like 1 second. And then speed would just be like,
Yeah, you're on it, you got it. Just what is, come on. I'm not gonna write it. Something over time.
change in volume over time? I don't know.
Let's talk about speed in general. What is
Change in distance.
yeah, distance. So I guess it's not I thought y'all would be more confused, but it's pretty simple. Yeah, flow rate is like the flow of volume over time, and speed is just distance over time, or change in distance over time. Bro, you got the harder question right, and then the easier one you like blinked. But it's okay, you got it. Honestly, I think that's it. Did I write the name for this? Okay, this thing, I need to see how you spell it. His name is like Poisel or something. Poisuli? What is it?
No. I just call it Pasuli's.
Poisuli's law. So this guy's law is relating to the whole flow rate thing with the viscosity, and then Bernoulli and Venturi are those things. Venturi is a specific form of Bernoulli, which is that tube thing that I just talked about. And yeah, bro, I'm sorry to get over this stupid chapter. All right, any questions? If I'm even able to answer them, I will try my best. But any questions or any clarifications y'all need? What is viscosity, guys? I didn't even describe what viscosity is. What is viscosity?
The resistance fluid has.
Yeah, resistance to flow, basically. Like if I have, this is a sideways tub, okay? And I have water in it. This is water. And then I have this one right here, and I have like honey. Which one is going, are they going to flow at the same rate? Or are they going to flow at different rates, or what? Like I'm trying to make it fall. Like which one's going to flow better? What
Water.
the heck? Yeah, water. Because honey is more viscous. As you can see, the viscosity is down here. If I have a higher viscosity, that means my denominator is bigger, which means my flow rate is going to drop. So that's how you can relate them. But Viscosity is kind of like friction, but for fluids. So like friction to motion of fluid, or just resistance to flow. That's all viscosity is. Okay, I think that's it. Once again, I think this chapter went fine, but like the best way to learn is to just struggle and practice problems. Then you'll eventually realize like where things apply, when to use them, and all that stuff. So yeah, one more time, any questions? Tomorrow will be better for sure. I actually like tomorrow's chapters. It's about like electrostatics and like circuits and stuff like that. And then after that, we're gonna do like optics and sound and all that stuff. So this is the consensus most hated chapter, I think. I think people don't like optics either, but I like optics, so that one's fine.